Statistical process control, attribute control charts. In this video, we will create so-called P charts, and these are an example of attribute control charts. There are other actually attribute control charts in the literature as well, but we will focus on the P charts, and they are useful when it is difficult to come up with a single variable that captures a degree of specification conformance. And then we can just track the percentage of defective items, right? P stands for percentage or proportion of defects. And of course, this could be, right, for example, percentage of customers that were dissatisfied with our service, or percentage of products that when final testing was performed had some problem and couldn't be sold as working units. Here, sample sizes are often much larger, right, for P charts, particularly if defects are relatively rare. So N is again a sample size, number of units that we test during each time period, and P will be percentage of defects, which will be calculated basically as number of defects divided by the sample size. So how many of those N units were actually defective? In order to set up, again, we will have two stages, right? We set up the charts once, we create a P chart using some, for example, 25 initial samples of data, right? When we set it up, we again calculate the central value, which is the mean value of all the P values. Remember, P is the percentage in one sample, and the P bar will be the average over 25 days of those P values. And here it's actually quite easy to calculate standard deviation. Standard deviation is P bar times 1 minus P bar divided by N, and we take the square root of that. And once we have this standard deviation or estimation of standard deviation, we can calculate the upper control limit as P bar plus 3 standard deviations, and lower control limit LCL as P bar minus 3 standard deviations. Now, because if sample sizes are small, this can be sometimes less than 0. Of course, the proportion can never be less than 0. So that's why I added here, take maximum of this value at 0. If this is negative, take 0 instead. So this is the setup. And again, as before, we have to control the process. So the idea is once we set the control chart, the P chart, using these calculations, we then are supposed to continue collecting samples. So for example, if we collect samples daily, we should again every day collect a sample of the same size N, calculate the percentage of the defects, right, in that sample, and add a point on the chart, so update the chart regularly every day, once a day, and then see if we're still within the control limits. If one day we're not, we have right, an alert through this. We have an alert that tells us there is something wrong in the process. Most likely there is something wrong in the process. Go investigate, find something that changed, right? Find an assignable cause for the variation that should not happen under normal circumstances. And maybe this way you detect a quality problem, and then in the future you avoid that quality problem. So again, let's consider an example. Suppose we collected data for 10 days, an initial sample rather than 25, and then the sample size was 1,000, right? So 1,000 randomly selected units are tested each day. Let's say this is for a large manufacturer. So suppose on these are the values collected on the 10 days. The number of defects out of 1,000 was 1, 1, 3, and so on, right? So we can calculate percentage as this number divided by 1,000. So that's going to be 0.001 and so on, right? 5 defects, 0.005, right? We can then calculate the mean over those 10 days, right? If you calculate the mean value here, it's 0.0022, and the standard deviation, which again can be calculated from this value, P bar times 1 minus P bar divided by N, and taking the square root is this. So we can now calculate the upper control limit, adding the 3 standard deviation estimations, or subtracting, but when we subtract 3 of those values, we actually are below 0. So we just take 0 in this example. And so after we set up the chart, it looks something like this, right? Here is the average, right, of value of P. Here is the upper control limit that we calculated. And here is the line on the 0, the line of the lower control limit. And of course, as we said, this grayish part here indicates in my chart the part for used the samples used for the setup. So now we need to control the chart and see what the new days, right, the number of defects on the following days will be. So suppose after 6 days, I collected the samples and I had the percentage defects, right, that was changing between 0 and actually 5, right, because this is a sample of 1,000. So this is 5 defects out of 1,000 gives me percentage of defects, right, 0.5% or 0.005. And the process appears to be in control because all the points that I'm seeing here are still within upper and lower control limits. Now, suppose this is day 7, right, after we set up the chart, so day 17 actually on this chart, and we see that percentage of defects was larger. We had actually 9 defects out of 1,000. And of course, this is more than the variability that we expected. We have a new point that is above the upper control limit, right? And so that point indicates that there must be a problem or the most likely is a problem in the process. This should not happen under normal circumstances due to common cause variations. This must be most likely assignable cause variation, and therefore we should go and investigate what happened in the process that created more than the usual number of defects. And if we investigate, we might discover some kind of problem that is causing quality issues, and then we might try to fix that problem and avoid quality problems in the future.